So we're going to talk now about gradient-based optimization. So basically the idea is we've got a black box, we've got inputs, we've got a black box, we've got some outputs, and we now want to, so if we come back to our schematic over here, we've got some inputs, we've got a function of some sort, we've got some outputs, and what we want to do is talk about what kind of an optimization algorithm could we develop that could use those inputs and outputs, the information from that, and keep looping on this and come up with and move towards the global optimum or a local optimum. You know, how can we make it smart to do that? And so we're going to first talk about these gradient-based methods. Okay, so gradient-based algorithms. There's a couple important terms that we're going to be using. The first one is gradient. What is a gradient? So I want to take a crack at that.
It's the vector of derivatives with respect to each design variable.
Okay, great. So it's a you can, this is almost synonymous with derivative. Okay, so it comes directly from, and derivative is basically synonymous with slope. You know, what's the slope of our design space at some point? So again, if we come back to just a one-dimensional, we've got an X input and Y output. And let's just put in some function here. And let's say that we're trying to find the point that minimizes, or you know, the point along here that minimizes Y. Well, this is a black box. We don't know where that point is, but we can start at some other point. So let's just say that we start up here. That's our initial guess. The gradient is basically, we can look at the slope. If we evaluated points next to our point of interest there, or our initial guess, then we could say, hey, you know, if I move to the left, they move downhill, right? So the gradient is really helpful for understanding what direction we need to walk to get closer to the minimum. What it doesn't tell us is how far we need to walk to get closer to that minimum, right? So the gradient will say, you know, you want to move in this direction, but how far? You know, if this is our initial X here, so we'll call this X naught as in our initial guess. For our X1, you know, for our next guess of where we want to go, we just know we want to be at some value smaller than X naught, but we don't know really how far to go. We just know that, you know, that direction goes downhill. Now you might be able to recognize one limitation of gradient-based algorithms just from what I've drawn here, and that is, what if I started at this point right here, right? What if that was my initial guess? And again, I just chose some initial guess location, and the gradient, although it's slight, is still downhill in that direction. I've got what's called a local minimum over here on the left-hand side. And so a gradient-based algorithm is going to, if my initial guess, if I start right here, it's going to end up with that point eventually, you know, as it continues to walk downhill, it's going to eventually find this other local minimum over here that's not the global minimum. And so in order to find the global minimum, we have to start our algorithm in the basin, in the same basin as where the global minimum is, right? That's gradient-based algorithms require, if you're trying to find the global minimum, you've got to start it in the correct basin. And so another way to think of that is just that for a gradient-based algorithm, you're always going to find the minimum of the basin that you are in. This is like a watershed, right? If you dropped some water at that location on Earth, where is it going to run to? Where's the lake or the pool that it's going to run into? And that may not be the global minimum on Earth. That's the local minimum, right? And gradient-based algorithms always find the local minimum. Okay, so the derivative or the gradient is really important to understand. Now, in one dimension, it's basically gives us a direction, left or right. But in two dimensions, if we were to say, well, this is our design space where we have x1 over here and x2 up here, the gradient basically tells us the direction to walk that is perpendicular to the local contour line. Okay, so like Corey was saying, that it's related to the derivative, but it's really a collection of derivatives of each of my design variables, x1, x2, xn, the number of design variables. It gives me a direction to walk that will be downhill from that point. Okay, that's perpendicular to the local contour line. Okay, but it doesn't tell us how far to walk, right? It just tells us a direction. So that you just have to remember that with a gradient, it tells us a direction, but not a distance, how far we want to go. Okay, another a concept that we're going to be talking about is called a Hessian. A Hessian. What's the Hessian? This is a little bit harder to explain, but any takers?
It's a matrix of second derivatives.
Okay, so I'm going to, again, I'm just going to say this is related to the second derivative. And let me pull up actually what the Hessian looks like. This is just off of Wikipedia. This is a Hessian matrix, but basically you have the derivative of a function relative to x, or the second derivative relative to x1, and then you've got these components in this matrix where you have the second derivative, the first one with respect to x1, the second one with respect to x2, or whatnot. Does that make sense? So this is an n by n dimensional matrix that tells us about the curvature or the second derivatives of this design space. All right. So again, I'm gonna say this is kind of related to curvature, and we're talking about this kind of in generalities because we're not going to do a lot of really specific. We're not going to dig into the math too much. I'm trying to help you understand this in more of a general sense, but let's come back over to our examples over here. So let's look at what this Hessian might tell us. So at this point that we were looking at here before, so we're talking about this point right there, the Hessian would tell us about what kind of a curvature. It's basically like fitting a parabola to the local information there. We could predict out, a distance away what the curvature is going to be because we know what the change in curvature is at our location. If we assume that this is kind of parabolic in nature, then we can predict what the curvature is or what the value is a little bit further away from our location. Just like the first derivative allows us to predict what the value is a little bit further away from our location, the second derivative gives us a more accurate estimate of what the value is at a certain location away from the derivative. Now, you may recognize that these are basically the first two terms in a Taylor series expansion about any point. If I know the first derivative and the second derivative at that point, then those are the first two terms of the Taylor series expansion, or really the first three terms, I guess, the first one being the value itself. And then we have the first derivative and the second derivative. And so basically what we have with this information is a representation in n dimensions of what the design space might look like. If we know the gradient and the Hessian at a single point, we can predict what it looks like really close by to us. Does that make sense? So the gradient tells us the local slope. The Hessian, though, from the Hessian, we're actually able to predict where a minimum might be, right? Because we know how what the curvature looks like locally. We know what the function is doing. And so that allows us to predict where a local minimum might be. Now, the function that I drew up here is a little bit nasty because we have major changes in curvature happening here, right? But if I had guessed, if my initial guess was right here, then you can see that it could have, based off of the Hessian, we would have guessed that the minimum was somewhere around that location, and we know what direction to walk from the gradient. So actually, we could very quickly converge to the minimum there, as long as the design space is truly second order in the region that we're talking about. Does that make sense? So this kind of information is really important for these gradient-based algorithms, and each of them use this information in different ways, the gradient and the Hessian. Okay, now one requirement that we have for gradient-based methods is that the design space is continuous. Okay, so for a gradient-based method to work well, we've got to have a design space that is continuous, and if they're continuous, then they just work a lot better for gradient-based methods. Now let's come over to these examples over here. All of these, I believe, are continuous design spaces. I didn't see any that were actually discontinuous. And by continuous, what we mean is that there's no actual, I'm not entirely sure that all of these are. We'd have to study them a little bit more. But anyway, basically, a continuous design space, the definition of that is simply that there is a continuous change from point A to point B. You have a continuous change in your output function. You don't have a step change anywhere, right? A cliff, so to speak. If we were to look at these contours, there's no cliffs here. We don't have a plateau that suddenly, if you change from the value of 1 to 1.00001 or something, that you have a step change in the value. It's all continuous, right? So gradient-based algorithms basically require that you have a continuous design space here, so they can walk around in them and work with gradients. The problem with a discontinuous design space, or a step change in the value, and that's easy to visualize, this would be a discontinuous space, is if you have something that looks like this, and then something like this, right? So there's a step change right here in value, and so it's really challenging then for a gradient-based algorithm. When it gets to a certain point that's discontinuous, it can't compute gradients, right? Because it needs to compute values at neighboring points. If it's doing the gradients numerically, it's got to be able to compute those at neighboring points, and it can't do that because there's a step change. So the gradient that it would get at that point would be very erroneous, or the second derivative that it might estimate at that point would be very erroneous because it's computing that numerically. Okay, so like I said, these gradient-based algorithms really require information about the gradient. Some of them require information about the Hessian, not all of them. But let's see, there we go. And you can get this information different ways. So for example, the gradient, any of these, the gradient or Hessian, you can estimate. I'll just say down here, we can estimate these basically two different ways. The first one being analytically. What if we actually have the function over here, right? So let's take this function, for example. It's not obvious to me where the minimum is of that function, right? Just looking at it, I have no idea what the value is. It's going to minimize that. But back to Kyler's earlier point, I could take the derivative of this function, and I can analytically compute that derivative at any x and y input value, right? So I could take the analytical derivative of this, and then I can plug in any xy value and get an analytic derivative. And there are some optimization cases or times when you'll be working with optimization where you actually have an analytic function and you can compute that analytically. And so many optimization algorithms will allow you to do that. If you know what the gradient is or the derivative is, it will allow you to write a function for that derivative. So you'd have a function for your actual objective function, and then you'd have a function for the derivative, and it will use that function to compute the derivative whenever it needs it. But if you don't provide that, then most optimization algorithms will compute or estimate these derivatives using finite differencing. Okay, so the first one here is analytic. And then the second method is through finite differencing. So if you don't provide an analytic derivative, which for most of the studies that we do in our lab, we don't have an analytic derivative, then instead, the way that we can estimate those derivatives is by computing the solution at two neighboring points or at one neighboring point and estimating the derivative off of that from finite differencing. Now, finite differencing, there are many different ways to do that even. And to save on computational expense, the default in many of these optimization algorithms is to use either forward or backwards differencing. And basically what that means is that if I've got some point here, so let's say we've got some point in this design space, I already know the value because I had to call the function once to get the value at that point, right? And so to estimate the gradient, I'm just going to add a little bit to my x value here and compute the value there, and that will allow me to estimate the gradient there, right? So that's called forward differencing. If I'm adding a little bit to x, it's called backwards differencing. If I'm subtracting a little bit from x, really, they're both the same amount of accurate. There's not really an advantage to forward over backwards, but most of them use forward differencing. But what's more accurate to evaluate that derivative is to use what's called central differencing, where I look at a point a little bit to the right and a little bit to the left, and that's called central differencing. However, it requires one extra call to evaluate the derivative, because I already know the derivative at the center. That's the point of interest, or excuse me, not the derivative, the value. And so now it's going to require two calls, one to the right and one to the left, in order to estimate the gradient there. The nice thing about central differencing is that this is second order accurate. And so it gives you a little bit more accuracy in that derivative, which can influence things throughout the process. So the default, whenever I run optimization, I always set this to central differencing. Just from the cases that I run, I'm happy to pay that computational expense. It costs a little bit more for the accuracy, but where that really matters is when you get close to the minimum, being able to use central differencing to estimate those derivatives is much more accurate than using forward differencing, because forward differencing, when you're close to the minimum, is going to have a little bit more error in it. And so to really hone in on the minimum, I find that I have to use central differencing. Okay, so that's usually an option in there that you can just set in a lot of these codes, and we'll see that, to ask it to use central instead of forward. Okay, so I prefer this one if you can handle the computational expense. Now, sometimes it's not worth it if your function requires a whole lot of computational power to run something. Sometimes you just want to use the forward differencing to cut down on the number of calls for the gradient based methods. Okay, so again, and everything that I've said here for the gradient also goes for the Hessian. So you can code up your own Hessian. If you have the analytics solution to your function, you can actually differentiate that analytically and write up a function that returns this entire Hessian matrix. If you don't do that, then the code, if it needs the Hessian, will be estimating that based off of either some kind of finite differencing, forward or backward or central or whatnot. It has different methods for estimating that derivative numerically. Okay, any questions on that? Okay, so I've got an exercise here for you guys. What I would like you to do is we're going to actually compute some stuff here. Okay. So what I'd like you to do is yeah.
Sorry, I had a question on discontinuities.
Mhm.
I put it in the chat, but I just wanted to ask, how sensitive are gradient methods to cliffs or discontinuities, and how do we expect optimization routines to behave if they run into cliffs?
Okay, good question. So let's move over here with our understanding of and let me just put in an example. This may not be a very good. Let me do this. Okay, so we're going to look at that design space. Okay, where there's a cliff here. So we've got our cliff here, and basically the challenge here. So let's look at two different scenarios. Let's look at a scenario where we start with a point over here. Okay, and so a gradient-based method is not going to have an issue if we start right here in this design space and happen to be moving in the right. So it's going to take the gradient, the Hessian, or whatever it wants. It's going to walk downhill, and eventually it's going to find the minimum. So it's not even going to know about the cliff on the other side, right? Because it never ran into it. But if and I didn't, I guess I didn't draw a very good example here. Maybe we need it to come up over here. So, okay, but if my guess was over here somewhere, then how is it gonna or move across this cliff, right? So it'll move downhill, and then all of a sudden it's going to get like this huge gradient, and the second derivative might have some curvature that looks something like that it's estimating, you know. So the problem is the gradients and the second derivative, they get thrown off significantly anytime you have a cliff. And so your best hope is that it can cross that cliff without jumping clear over to some other point because of what it thinks the first and second derivatives are. Does that make sense? So you're hoping that it can navigate moving across that cliff and then end up in this basin here somehow. Now, a very common issue is that your cliff is exactly at the bottom of your function here. Okay, so there's a very common issue where you have a step change, and that you want to settle right up against that cliff, and that cliff can be caused by either the objective function, or it can actually be caused by a constraint, that you're going to violate a constraint, right? And so the challenge here is that as you get closer to that point, it needs, again, to compute points on both sides of that. And actually, I didn't draw that in the right place. So you're going to have a point there and a point there. And based off of that, it's trying to estimate a first and second derivative with neighboring information. And so, if you fit a parabola to this, it's probably going to look, something like this, and say that your minimum is a little bit off of that cliff. Does that make sense? That your actual minimum isn't right up against that cliff. And so it can have some numerical challenges getting right up against that cliff. It's always going to be pushed away from the cliff, I guess is what I'm trying to say. If you're trying to find a minimum that actually is right at the base of the cliff, it's going to push it away because it's going to keep estimating that the minimum to that parabola is a little bit to the right of the cliff. So anyway, those are just some examples. Of course, if you have a design space littered, so for example, what if you have a design space that looks something like this? That's just a nightmare for gradient-based optimization, because it's using neighboring information to get gradients. So as it crosses a cliff, it says, oh, there's a huge gradient here, right? But then it moves a little bit more to the left, and it says, oh, the gradient is 0. I don't have any change in my function, or so they're very small. So you go from big gradients to little gradients, and then your Hessian is all messed up. And anyway, those are the kinds of problems with it. So.
Okay.
Did that answer your question?
Yeah, it does. I think we could talk more later, but I think that's something that's going wrong in my stuff that we talked about. So
Okay.
that's helpful. Thanks.
Okay. Yeah. Okay, so here's your exercise here. So I'd like you to use the function z equals x minus 5 squared plus 4 times y minus 2 squared. Okay, and number one, I want you to use Excel to visualize the design space. And then number two, I'd like you to start with an initial guess of, let's see, -2, 2, okay? So at some point in the design space, again, the optimization algorithm doesn't have access to this visualization like you do, but I'd like you to be able to visualize what's going on here, okay? And I would like you then to compute the gradient. I'd like you to do it two ways, analytically and numerically. Okay, using finite differencing. And then we'll come back. So the gradient, maybe we need a definition of the gradient here. I know I showed one for the Hessian, but for the gradient, so this is going to be, the gradient is a vector, and it's going to be the change in your function with respect to x1, for example, in our case, and then the change in the function with respect to x2. Okay, so that's the gradient of the function. Did I get that right? I just pulled that off the top of my head. Anyone want to correct me on the gradient?
I think you're correct there.
Okay. Okay, great. So let's work through these. Let's take about 5 minutes. Go ahead and visualize the design space. And then at this point, -2, 2, compute the gradient analytically and numerically.